So let's see what this question is telling us. It is giving us information about the failure of these two chords right here. This is one chord, and this is another one. And it is saying that based on this equilibrium that we see, find the maximum weight of the crate right here. This problem is important because we will be using pulleys in practice, and we will also apply the knowledge we have learned in the previous videos. So starting off, we want to ask ourselves, how do we approach a particle equilibrium question? The answer should be is to draw a free body diagram. So let's do that right here. Let's look at these elements. We have a pulley here. We have a crate. We have this rigid ring and another ring here. So let's pick which element we should be drawing a free body diagram for. Clearly, we want to pick the pulley. The rest of these three elements don't really give us that much information because let's say we were to draw the free body diagram of the crate. It would just look like this, where this is the weight of the crate and this is the tension T. It might help to draw it if you are struggling to visualize things, but what we're really interested in is the free body diagram for this pulley right here. So let's draw it. This is our particle, the pulley itself, and we have a force in this direction. We have a force in this direction, and we have a force in this direction. This is evident because when we look at the pulley, there are three cords that are connected to it. Now, let's define our axes. This is the horizontal axis, so our x-axis, and this is the y-axis, the vertical axis. I'm going to extend this x-axis here so that we can define this angle theta, and I'm going to call this force D. I'm going to call this force C, and I'm going to call this force A. Now, when we look at this question, now we have converted the information in this question into a diagram. However, we are not completely done. There is one more piece of information that is given, which will be significant. This triangle is significant because it can give us information on how to find the components of vector C, of the two-dimensional vector C. So this is 12, this is 13, and this is 5. Let's call this angle alpha, and we will see that angle alpha is correspondingly here in our free body diagram. And now we have a system that we can solve. So off the bat, it might not look like the answer is straightforward because it is not. The answer is not straightforward, but let's try to solve this system that we have drawn here and see if we can get any useful things out of it. So I will do that now. We start with the summation of forces in the x direction equals 0, and the summation of forces in the y direction equals 0. So let's do x first and then y second. Oh, before I do that though, I do want to mention one thing. Since this is a pulley system, the magnitude of vector A is the same as the magnitude of vector C. This is pretty evident because this is a pulley and this is the same string, which means that this vector, this force right here, is the same magnitude as this force. We have vector C, and it has an x component that looks like this. So let's have vector C times sine alpha minus vector D times cosine theta equals 0, because the net force in the x direction is supposed to be 0 because we're in equilibrium. Let's do the same thing with the y direction. I'm going to scroll down. We have vector A and a negative sign in front of it because it's pointing downwards, and we defined our axes as positive y pointing upwards. So we have negative A because it's pointing downwards minus C times cosine alpha plus D times sine theta equals 0. So now we've got two equations. What I want to do now is use this expression to our advantage, because that will simplify these equations right here. So I think previously I did say that we do not need a free body diagram for the crate, but it might be helpful to do that. So I will now draw a free body diagram. Once you get comfortable with these, you probably will not need to draw one, but it's always better to draw it if you're unsure. So let's call this vector the weight of the crate, denoted with a W, and we have vector A pointing upwards. So let's think about this. This is the crate. I'm going to use a different color. This is the crate, and one of the forces acting on it is obviously its weight. And what is preventing this crate from falling down is the vector A, which is equal in magnitude to vector W. Because when they cancel each other out, there is no net force. And since we know that F equals ma, if F is 0, then acceleration becomes 0. So now we see something else. We see that the weight of the crate, defined as such, the magnitude of it, is equal to the magnitude of A, and that is equal to the magnitude of C. So let's simplify these two equations using this thing that we just figured out. The equations become, so let's start with this one. That one becomes W times sine alpha minus D times cosine theta is 0. So now let's get this one and simplify it. That one becomes negative W minus W times cosine alpha plus D times sine theta is equal to 0. When we look at this equation, we see many unknowns, but we actually do know some of this stuff. So we know what sine alpha is and cosine alpha is because we defined that triangle up here. So let's determine what is sine alpha and cosine alpha. Sine alpha, I'm going to write it down here. Sine alpha is 5 over 13, and cosine alpha is 12 over 13. Now let's go ahead and simplify these equations. Okay, now let's interpret what these equations mean. This equation will make sense if we refer to our free body diagram, which I will draw again because we simplified it in a way. So this is W, and this vector is also W, and we have a vector called vector D, which makes an angle theta to the x-axis, and this guy makes an angle alpha to the y-axis. So what is the question asking us? Why do we care about this free body diagram? The question is asking us, let's see, if we have a maximum load of 100 pounds on the cords, not the crate, but the cords, determine the maximum weight of the crate, so it wants us to determine the weight of this, and the angle theta for equilibrium. So let's scroll back to our free body diagram. It is asking us to determine W and also to determine theta. So there's a way to do that. However, before we do it, I want to write down the maximum tension. The maximum tension is equal to 100 pounds. This is important to recognize because if we don't look at this problem, we do not know where this 100 is going. So here's what I'm saying. In our pulley system, there are two cords. I will show the first one in green. This is the first chord, goes all around. And this green chord is all one chord. Let's look at our second chord, which I will show with blue. It looks like this. And both of these chords, both the blue one and the green one, have a maximum tension of 100 pounds. What we have to do is to figure out which one of these chords, the blue one or the green one, fails first. To determine that, we ask ourselves a very straightforward question. Where is the tension coming from? What is causing the tension? Let's look at our diagram. Clearly, the crate is causing the tension. So let's scroll back down. The crate has a weight, and this weight is pointed downwards. Weight pointed downwards right here. Accompanying this downward force, there is another downward force, which comes from here. This has magnitude W, as you can see in the free body diagram. And the vertical component of this vector contributes to the downward force that happens here. So let's look at this. If this is our vector W, so this guy right here that I've just circled, this has a vertical component and a horizontal component. The downward vertical force is Wy, so Wy plus this guy, so W. Opposing that is the blue chord that I drew on this pulley, which has a vertical component. Let's draw that one out too. So this is, let's say, vector D. And this has a vertical component, dy, and a horizontal component, dx. So in order for there to be equilibrium, the magnitude of d has to equal this expression here. So what we're basically doing is two chords, this one and that one, fighting the equilibrium downwards, whereas we have one chord fighting the equilibrium upwards. 2 versus 1. D will fail first. Okay, I just realized that I made a mistake. I meant dy, so the vertical component of D. We're only looking at dy equals Wy plus W. To support this point further, I will draw an imaginary pulley that isn't the one in this example. I will draw an imaginary one to support my point. So let's say that this is our new vector f, and we have this vector called vector t. And then we have the other side of the string pointing downwards as well, and we will also call this t. So we have two t's working downwards. It's working downwards. And we have f working upwards. It's working upwards. If I say that this string and that string both fail at 50 pounds, they fail at 50 pounds, which one fails first? Let's say F is 49 pounds. What would T be? Clearly, T would equal 49 pounds over 2, which is equal to 24.5 pounds. So if I add one more pound to T, let's say instead of 24.5, I pull down on this tension, on this cord a bit more. I pull down a bit more, and T becomes 25.5 pounds. I added one more pound. Then which would fail first, T or F? Clearly, F would now become 51 pounds. It has failed. So the same logic applies here to our problem right here. If there's a dy for our vector d, so let's sketch dy. This is dy for our pulley here, right? By that logic, the blue string, so the string accompanying vector d, would fail first. So what we just did is look at the problem and see what it's talking about, understand what it's talking about, and now we are in a position to solve it. We realized that the chord accompanying D will fail before the chord accompanying W. There are two chords, and we just discussed that D would fail before W. Very important. So now let's get the maximum load and replace D with the maximum load. What you will notice is that this substitution that gave us these two equations has two unknowns per equation. There's W and theta. W, theta. Let's simplify this further. By looking at the question and understanding what it is talking about, we have gotten this equation, or these two equations, so this one and this one. We have C, D, alpha, theta, A, and all that crap. We basically simplified it down to two equations that have two unknowns in them. And we did this because we looked at the question and we understood what it's talking about. The rest of this is just basic algebra. And what you will notice is throughout the vast majority of this course, this trend will follow. The algebra will be very easy. The calculations will be easy. All you have to do is look at the problem and understand what it's talking about. So now let's solve this expression. We see a cosine and a sine. What this reminds us of is tangent of theta is equal to sine theta over cosine theta. So let's get these equations and let's find expressions for sine theta and cosine theta. And now let's use these expressions and combine them into forming tangent theta equals 25w over 5w, which simplifies to 5. So using the, by calculating the arctangent of 5, we get 78.7 degrees. So one part of the question has already been answered. Finally, let's move on to the second part of the question, which is to find weight. Now that we know what theta is, we can use one of these two equations. I will use cosine. So cosine of 78.7 equals 5w over 1300, which will give us w equals 50.9 pounds. And that is the second part of this example. And we have successfully solved this question.